Hello there, I'm Thomas Hatsios, the British American pilot flying the Boeing 777-300ER original flight from Zurich International Airport. We're going to be flying Zurich, Switzerland, Germany, next coming back to the Zurich International Airport, runway 14 for an ILS localizer. Landing surrounding the cockpit for the pre-takeoff preparation of the Boeing 777-300 ERX of the Pmdg simulation and Microsoft Flight Simulator X. I'm going to start showing you the cockpit instruments and the displays, like the primary flight display. That displays the airspeed indicated, the ground speed, the airspeed selected from the autopilot and flight director system panel, the radio altitude above the ground level, the barometric altitude above the sea level, the barometric pressure of the outside atmosphere, the target altitude selected from the autopilot and flight director system panel, the rate of climb descent of the aircraft in the VSI tape, the vertical speed indicator. We have the magnetic North Pole and the true North Pole and the magnetic variation depending on where we are in the world. We have the altitude indicator the pitch ladder in degrees and the bank angle in degrees. Also we have the flight director crossbars for manual guidance of the aircraft with the ILS localizer crossbars, and also we have the autopilot crossbars for automatic guidance of the aircraft. We have the angle of attack of the aircraft as it flies, and also the flight mode annunciator with the autopilot and the auto throttle, later on vertical navigation modes. We have the navigation display that displays the airports, the waypoints, the GPS position of the aircraft, the RMP and the LT, the required navigation performance and the acquired navigation performance. We have again the magnetic North Pole and the true North Pole and the magnetic variation depending on where we are in the world. We have also the weather radar reflections with the terrain reflections, and you can see the terrain elevation levels with red, yellow and green, and also with blue you can see the lakes, the rivers and the sea. You can see the airport names, codes, and also we have again the magnetic heading address, and we have the wind direction and vector and speed, and also the next waypoint we're going to be overflying. So we're going to make a complete route using the flight management computer by using the inputs of the aircraft data, like its takeoff weight, the fuel on board, the passengers and the cargo on board. And we're going to make calculations about the takeoff speeds and also the center of gravity of the aircraft and the horizontal stabilizer frame. So we're gonna use also the runway. We're gonna use for takeoff the data of the runway length, the elevation above the sea level with the barometric pressure and the barometric and the atmospheric density and the temperature of the atmosphere, and also the wind direction and airspeed. So we're gonna make these calculations, and then we're gonna input the seeds, the standard instrument departures from the runway. We're gonna select on the airport. We're gonna select the intermediate waypoints and features and the destination airport and runway with the stars, the standard terminal arrival features and waypoints, and the ILS localizer for the destination runway. So we're gonna make a complete route for the later on vertical navigation profile of the aircraft. We're gonna use manually or using the autopilot and flight director system panel and the auto thrust. So I'm gonna show you how to do that. We're gonna have the flight plan using the flight management computer. You can see the flight management computer over here. The primary flight display, the navigation display, the upper and the lower ACAS and indication accelerator system, and the autopilot and flight director system panel. The yoke, the flight controls of the aircraft and the rudder pedals, and also the thrust levers over here we use for manual thrust settings. So I'm gonna show you after that the autopilot and flight director system panel that contains the autopilot engage and disengage switches. The flight director engage and disengage switch, the auto throttle left and auto throttle right, engage and disengage switch. The airspeed select node for the airspeed guidance of the aircraft. We select the airspeed in nautical miles per hour, knot, or Mach speed, and we select the modes like the flight level change, the auto thrust with speed, and also the climb continues. So we have some modes like the fixed thrust mode, like the takeoff go around and the climb continues, and also the idle thrust for descent, which are fixed thrust modes. So the airspeed is being adjusted by controlling the rate of climb or of descent of the aircraft by using the horizontal elevator stabilizer chain orders from the autopilot to flight director system panel, and having fixed thrust from the auto thrust system that commands the FAREX authority to use electronic control computers one installed per engine. So I'll talk to you about later about the FAREX and about the engine. We also have the variable thrust modes like the cruise and the approach and land mode. So I'm gonna show you also that we have the LNAV and the VNAV, the lateral navigation and the vertical navigation of the aircraft, which is interconnected by the flight management computer, which takes the inputs of the flight plan we create. We have also the bank angle hold switch. We have the heading select knob and the heading hold switch. We have the VSI vertical speed indicator, and we have this mode, the flight path angle for a trigonometric angle increase for the climb of the descent of the aircraft, and also the vertical speed selector like tens, hundreds, or thousands of feet per minute for climb or descent. Then I'm going to show you the altitude hold switch and the altitude select knob, and also we have the board localizer for an ILS localizer approach, and the autoland function using the approach switch of the autopilot and flight director system panel of the Boeing 777-300ER airplane. Then I'm gonna show you, as I told you, the upper and the lower ACAS engine indication and alert system display that displays permanently the upper ACAS displays the engine indication. Also, I'm gonna show you the thrust levers of the aircraft we use for controlling the engine thrust. We have two engines installed in the Boeing 777-300ER, two General Electric 90 turbofan turbocharged engines, which are very powerful and produce a lot of thrust for this jetliner aircraft. So we have one left wing, one right wing for symmetrical thrust and redundancy, and also I'm gonna show you then. I'm gonna talk to you about the flight theory of the aircraft, about the newtons per second and third law of kinematics of motion, and the Bernoulli theory of fluid, and the aerospace and aeronautical engineering principles. Then I'm gonna show you the flight controls, how to control the aircraft using the flight controls, the yoke, the horizontal elevator, the stabilizer, and also the horizontal trim stabilizer, and also the ailerons and the spoilers, and also the rudder pedal for the vertical stabilizer. So we use the control wheel for the ailerons and the spoilers, and also we have the nose wheel steering the tiller for the ground control of the aircraft. Then I'm gonna show you the overhead panel, the electrical system, the left and the right engine driven IDGs, the backup electrical generators, the APU, the auxiliary power unit we need for starting the engines in the ground that produce alternate current 75,000, 130,000 kilovolts or 100,000 watts of 400 pairs alternate current, 120 to 100 volts. Which is having an electromagnetic alternator. So I'm going to say also the battery, the primary 38 volts, 48 ampere hours, and the APU battery, the primary flight control computers, the ADIRU, the air data analysis reference unit, that controls and displays all the air data using the primary and the navigation display and the GPS position. I'm gonna show you also the hydraulic system of the aircraft. The hydraulic pumps, the left and the right engine driven, the C1 and C2 electrically driven, which are also pressurized by the bleeder from the engines. I'm gonna show you the electronic engine control for the engine. So you see the other side system, the fuel of the fuel tanks, the center, the left wing and the right wing, and also the fuel transfer pumps, the forward and the up, and also the cross-feed valves and the low and the high pressure fuel valves for the engines. And also I'm going to show you the wing and engine guidelines, the cabin pressurization system of the aircraft, and also the bleeder, the pressurizer from the engines and from the APU unit, from the engines for cabin pressurization, wing and engine guidelines, air conditioning and ventilation, and also for the hydraulic fluid tanks pressurization, which are used for the flight controls and for other systems like the parking brakes and the landing gear external retract and the nose steering. So I'm gonna show you also the bleeder from the APU unit for mainly for starting the engines in the ground as a backup in the air. So this is all for right now. I'm gonna continue now with the cockpit. Thank you very much one more time for joining me in this video. I'm Thomas Hatsios, the British American pilot flying the Boeing 777-300ER into night flight. So I'm gonna start now with this with the panels of the Boeing 777 and the instruments, also the overhead panel you can see here, also the outside view of the aircraft. So we have about an hour, exactly 1 hour left for this flight. So I'm gonna start now with the primary flight display over here. You can see the airspeed indicated, the airspeed tape, the ground speed, the airspeed selected from the autopilot and flight director system panel. We have the barometric altitude above the sea level, 1430 feet. The terrain elevation you can see also here in the navigation display, and also the radio altitude above the ground level, the magnetic north pole and the true north pole here and here, and the magnetic variation depending on where we are in the world. So you can set magnetic north pole or geographic north pole here, the true north pole, by switching these two indications here to normal magnetic. So you can set also inches of mercury or meters over here for display. So you have the altitude also in meters, the altitude selected, and this is the airspeed selected from the autopilot flight director system panel. The pitch ladder in degrees, you can see 2.5 degrees peak marks, 2.5, 5, 7.5, 10. It goes all the way up to 20 plus or minus, and the bank angle in degrees like 45, 33 or less. So you can see here we're gonna select different values for that. We have the auto throttle left over here. You can see the auto throttle displayed with yellow. This off, the left auto throttle. Now we have the auto throttle right. You will see the auto throttle right over here. So you can see here we have also the displays here. I will show you later. Flight controls. So we have if we have a failure, for instance, something happens, the normal menu. So we have the synoptics, and you can use this here. The engine over here for display. So So we're gonna have the endings later. We need this display for the upper and the lower ACAS, Boeing 777. So we have the auto throttle right, the flight director on and off, the flight level change, the autopilot disconnect. So we use the flight director on and on here, both flight director left and right. So it is depressible also. We'll set an airspeed like this, indicated airspeed or Mach, the auto thrust, the hold switch, the climb continues over here, the LNAV and the VNAV, the angle of the aircraft as it flies, so the bang angle limit. We have also this hold, selecting the select and select heading or track. We're gonna select the runway right now. Also the hold switch for that. I'm gonna select an altitude, different altitude higher than that, like 35,300. You can see also this is the depressible, either mode, and the vertical speed at that angle. So like this, maybe we can set also the autopilot on, just for display. So you see the AP now is on, 253 nautical miles per hour, 7,710 meters, or 35,300 feet, heading, hold and flight level change speed. You can see the flight mode annunciator, again the flight director, and the heading 136 degrees here, and the vertical rate of climb and descent. You will see the needle moving up if we climb, or moving down if we descend. So we set again the barometric pressure in inches of mercury. We're gonna set now the altitude hold instead of the flight level change. You will see altitude over here for the climb mode of the aircraft. So also you can set the vertical speed, flight path angle like this. So you'll see the negative or positive flight path angle like this by moving the slider up and down. So, and we're gonna have like 3 points for the minus in front, and you will see the indication here in the flight director is below the horizon line, the tick marks. So this is the target descent rate from the cruise level. If we need to descend, if we need to climb, we go in the other way, in the positive, using again the slider. So you'll see the plus 3.5 degrees flight path angle over here, and you will see the positive over here, the climb, the tick marks over here in the positive side above the horizon line. So you have the flight path angle here, this mode for this target altitude, this target airspeed. So again, maybe we can set descent rate of minus 2,800. You will see over here in the vertical rate of climb and descent. And if we set the plus now, a positive climb, so you will see like 2,200 over here, the tick mark over here for the positive climb in tens, hundreds and thousands of feet per minute. So the needle will move all the way up here after the takeoff in the VS, the vertical speed mode, with the heading hold. We can set also again, we can set the autopilot disengage now. So we press this switch, you will see the warning here. Flight director, the primary flight display, and the autopilot is disconnected with the red letter. We rearm again, cancel the warnings. So we need to come here and press this switch. You will see the green light on, and now we can use this switch here. Press one more time and you see the autopilot again is disconnected, and press one more time, you will see the confirmation. So it disconnects completely. So this is all for the autopilot and flight director system panel. Maybe we can make now the rest of the systems, like the thrust levers. You will see here we have this is the autopilot disconnect, the aileron trim, this is control column and yoke. So this is the horizontal trim of the horizontal tail, stabilizer, the rudder pedals. So we have the position here of the horizontal tail, trim, stabilizer up and down. You can see the green band is mainly for takeoff, so the normal alternate control pads. We have also the speed brakes, which extend when the engines are idle. Over here you cannot extend like this. So also you have this is if you have a failure of the C or the R of the auto trim, the hydraulic system, you only have the manual trim after. You lose the autopilot and the auto throttle trim order. So you see the C and the R, the hydraulic system, normal or catal, which is concerned with this hydraulic, the C and the R over here. I will show you later. So you can see also we have the flaps position here, down or up. Before showing you the thrust levers, so you will see the flaps over here, 30 degrees, and it's moving down from like 20 degrees. I will tell you about the rest of the stuff now around the cockpit. You can see we have the fuel control for the engine, the left and right engine, cut-out switch, the fire extinguishers for the left and right engine. We have the parking brakes turn down like this. We have the weather and terrain reflections, the radar of the aircraft. We have also the TICA system, the traffic collision alert, that receives and transmits our position and receives from other aircraft or the traffic control. The ATSP and ATC transponder, you can see here the warnings, so you can test this, and then after in flight you might gonna see other traffic coming in. You see the warning and the resolution advisory. So you also have other navigation communication panel, transmitter, receiver, the left and the right engine, the electrical, the hydraulic, the fuel pumps and tanks, electronic engine control for the engines, and the bleeder, the pressurizer from the engine and the APU, the primary flight control computers and the ADIRU, the air data and Lszh reference unit that controls and displays all the air data you see here. So I will come again, I'll show you the auto throttle here with the autopilot and the flight director. So this is the auto throttle disconnect over here. and you take over the engine control. You have also the takeoff go around, so you can move the thrust levers forward. If you have the speed brakes, they will retract. You have them extended at the idle, so you can see the thrust levers position, the commanded and the actual, that takes some time for the engines to increase or decrease. You have also the limits of 104.6% of the rotation speed, the green, yellow, and the red. So I will start explaining them a bit more detail now. So I will have to explain about the N1. The N2 and the other indications. So you can see here we have again another nice view of the panel and the cockpit, also the outside view. You can see where we are right now. The runways of the Zurich airport. So this is the Boeing 777. So also, the thrust levers I talked to you about how to indicate the thrust produced. So you can see the N1, which is the low speed starter and the low pressure compressor and turbine of the turbofan turbocharged engine. We have the G90 General Electric 90, as I told you. Exhaust gas temperature per engine left and right. This is the idle thrust, now 32%. The bleeder pressurizer from the engine, which goes for the cabin pressurization system from the fifth and United States. The total fuel on board and the minimum fuel temperature. Also the flaps here, some other indications, warnings. So we have the landing gear, the normal, the alternate gear here, the blues on the normal gear, the auto brake, is exit takeoff. You can see the auto brakes here, the flap limit, and also the extended retract for mainly for this for the landing gear. So the rest is here. You have the N2, which is the high speed starter and stuff, the high pressure compressor and turbine of the turbofan turbocharged engine, the left and right, the fuel flow per engine per hour in thousands of pounds right now, or thousands of kilograms, the oil pressure, oil temperature, oil quantity, and the vibration of the N2 states of the engine. So we have the engines here. You will see now you can use a differential thrust like this. Move one engine at a time. We have like a failure in 5. So you see one engine is moving higher while the other remains at idle. Also we can use the other side engine now. So this is the differential thrust. You can use as much as you need. You see again now the other side engine, now it goes up while the other The left remains at idle, the right goes up like 43%. So we can move both at idle. If we have the thrust levers at idle, you can extend the speed brakes. Also, if you move them forward when they are extended, the speed brakes retracts automatically. Also, if we need to use the thrust reverse and the speed brakes extend automatically, you give a signal. So now we have the thrust reverser, which opens blocker doors and reverse the flow of the air from the turbo engines, and you can see here both turbo engines are open in terms of the bypasser. Also the speed brake extender, you can retract like this. So again, if you need to see the thrust reverse open like this, the blocker doors open. So again, you can retract like this. You see the speed brakes also retract and extend. So this will slow the aircraft in the landing phase. Also the other side like this, and extend again, and from behind. So I will show you now. I will talk to you now about the thrust levers function, about the flight theory of the aircraft. So we have like 30 more minutes left for this, for taking off the aircraft. So as I told you, we use the thrust levers to command the thrust. These are from the engine for achieving an airspeed inside. So we have the General Electric, as I told you, the 90 installing one in our Boeing 300 ER. One in the left wing, one in the right wing for symmetrical thrust and redundancy. They produce a lot of thrust because they are turbojet engines. So also we use the thrust levers in their connection with the autopilot flight director system panel and the auto throttle and the auto thrust system, and also the flight management computer, the Navina function, the lateral navigation, the vertical navigation mode, and also any mode we use in the autopilot, like flight level change or the vertical speed or the altitude hold. So the upper and the lower ACAS, you can see the engines also have a gearbox that contains the fabrics. The fabrics are the full authority to use the electronic control computers, one installed per engine. For the controls and displays of the engine's indications that you see in the upper and the lower display. So one installed per engine, dual channel redundancy, one channel phase, the other takes over. The fabrics are the full authority to electronic control computers that controls the displays and monitors or indications, like the N1, which is low speed starter and starts low pressure, compressor and turbine. The left and the right engine, the exhaust gas temperature per engine, the N2, which is the high speed starter and starts the high pressure compressor and turbine of the turbo-contributed engine, fuel flow per engine per hour, thousands of kilograms or thousands of pounds. Also the oil pressure, oil quantity and oil temperature, and the vibration of the N2 stage of the engine. Also they control and monitor the engine start, engine side on. The pressurizer from the left and right engine from the 5th and the 9th stage of the blade of the starters and the turbine and compressor. So if we have an overpressure inside the engine, they can open the bleeder valves into a higher stage, so they can relieve the overpressure from inside the engine. We have an under pressure, they can close to a lower settings, so they can increase the pressure inside the engine. Also this is necessary if we climb or descend to higher or lower altitude. they regulate the fuel air mixture. So if we climb from the sea level higher altitude, we have lower air pressure, air density, oxygen level. It's about half that of the sea level. If we go in the altitude of like 20, 30 or 40,000 feet above the sea level, where the cruise altitude is, we have half the barometric pressure and density of the air, and also the oxygen level. Also, the aircraft flies like in airspeed like 2 or 3 times faster than that of the sea level, so the intake of the air mass from the front of the engines of the turbocentrifugal engines is much faster than that of the sea level, so we need a different fuel air mixture every second for the aircraft if we climb or if we descend. So instead of doing this manually, we use the FATEX with full authority, the electronic computers to do that. So they optimize, as you can see, the fuel efficiency of the aircraft and the safety. So you can see here we have one landing, another aircraft just landed here. So I will talk to you now about the flight theory of the aircraft, about how to use, how to calculate the takeoff speeds, and also using the factors of the gross weight and the flight management computers. I will show you later. So So we have like 15 more minutes left for that. I will talk to you about the Newton's first, second, and third laws, kinematics of motion, the Bernoulli theory of fluids, and aeronautical and aerospace engineering, and physics and mathematics, and derive some interesting equations and factors about the flight theory of the aircraft. So about this aircraft, right now we have 254,000 kilograms of takeoff weight, or 531,000 pounds, which is below the maximum takeoff weight. We have about 46,000 kilograms or 104,000 pounds of fuel on board, about 30% in the left and right wing engines, standard times to So we have also 30,000 kilograms of passenger cargo on board, so in total we have 254,000 kilograms or 531,000 pounds. So we need to use for this runway length and conditions like wet, dry or ice, and the wind speed and direction, and also the pressure of the air and the temperature of the air and the density. So we need to use 15 degrees of flaps and 4 degrees of horizontal trim stabilizer just to take off, and we need to achieve an airspeed of about 154 nautical miles per hour, or 154 knots, or 270 kilometers an hour just for takeoff. We need to overcome the stall speed. The stall speed is going to make the aircraft wings not produce the necessary lift force. The lift is the force that makes the aircraft wings aerodynamic flow of the airstream of air around the wing. It's gonna make the lift. The lift is the force that overcomes the weight of the aircraft. The weight is the mass of the aircraft times the aircraft acceleration, depending on where we are in the world, and also the thrust from the engines, from the turbocentrifugal engines, overcomes the kinetic and static friction in the aircraft. So I'll show you now the outside view and talk with you a little bit about this, and then come inside. So you can see here we have the aircraft and the view of the aircraft. You can see the wings of the aircraft that hold the weight of the aircraft in total, and also the thrust from the engines move the aircraft forward. You can see we have this axis, the wingtip to wingtip, the lateral. We have this, the longitudinal axis, and we have the vertical axis through the center of gravity. You can see we have the mean aerodynamic chord position, about 85% of the wing chord, which is the maximum aerodynamic lift and center of pressure, and also where the stall of the wings begins, where the airflow becomes detached from the top surface of the wings. Also, this is a position where the center of gravity usually has been positioned for this airline. You can shift the center of gravity forward or after by moving passengers and cargo. So you can see the thrust from the engines moves the aircraft forward, only forward. So you can see we have also the center of gravity. We have the moment arm, it's times the distance from the center of gravity all the way back to the vertical or the horizontal tail. We'll talk to you now over the surface area of the horizontal or the vertical tail, times the airflow of the air mass per second, times the acceleration of the air gravity, and you have the lever arm or moment arm. You can pitch up and pitch down or make turns left and make turns right. Also you use moment arms from the center of gravity, left and the right wing. So now I'm coming to the wings. You can see the bottom surface of the wings is more flat. So as the aircraft accelerates forward, the airflow that comes is moving slower below the wing. So the airflow is more pressurized. We have higher positive air pressure below the wing, which pressurizes the wings of the aircraft up into the air. So we have differential pressure. You can see the top surface of the wings is more curved, it has higher curvature. So using the Bernoulli theory of fluid again, for below and for above, the Bernoulli theory of fluid, you can see the airflow of the air mass is moving much faster above the wings, so we have lower air pressure, negative air pressure above the wings, which sucks the aircraft weight and wings up into the air. So we have positive higher air pressure below the wing and negative above the wing. So this is all the theories we need for this aircraft. Now I'm gonna come to the flight controls. I will explain you about the flight controls, the theory. We have like 12 more minutes for that. So I will talk to you now about the flight controls. So you have, I'm using the side stick control, the flight controls of the Boeing 777-300ER in this simulation. So you can see here I'm having this side stick, the Lszh Extreme 3D. So I'm using this. So you can see the yoke here. So you can see the side stick, the deflection. I can climb or I can descend, move the horizontal elevator up and down. Also I can bankroll left and right using the ailerons and the spoilers. Also this is interconnected with the other side. Both move the same way simultaneously. So you can see the side stick deflection is proportional to the yoke over here deflection. Also I can use the rudder pedals for the vertical rudder, left and right. Also I can use the horizontal trim stabilizer. I show you here the trim tab pits up and pits down here and here the aircraft horizontal tail. So we have full flight controls. You can see the side stick deflection is proportional to the yoke deflection. You can leave neutral also. And also I'm having the thrust levers here like this. I can move the thrust levers forward and aft and actuate the thrust produced by the engines like this. So I'm gonna show you now the outside view and then come inside for making the engine start demonstration. So you can see here again. So you can see now the outside view of the flight controls and the side stick function for controlling the flight controls of the aircraft. So you can see again, I can climb, I can descend, I can make turns left and turns right, also hold neutral. So I have full flight control using this. I can climb, descend, also use the rudder pedals, also horizontal trim stabilizer. So this is all the function. Again, the thrust from the engines. So this is all for this now. Now I'm gonna come to the making the engine start demonstration. Also, you first the overhead panel and the lower display of the ACAS system. So we have like 10 more minutes for this. So I will have to show you over here. So you can see here we have the panel, we have the cockpit, this nicer view. It shows more stuff. So you can see we have the hydraulic fluid for the flight controls, disconnect switch here for ground maintenance. We have the circuit breakers you can reset in flight if you have an electric failure. You have the same controls in this place again here. So we set flaps 20, 15 degrees. You will see the 15 degrees over here. You can see again the speed brakes and thrust levers. Everything is having a nicer maybe view. You can see again the displays, everything is normal, and also the autopilot flight director system panel, this view. So we have here the ADIL, the air data index, our reference unit, the controls and displays all the air data, airspeed, altitude, rate of climb, descent, the gyroscopic acceleration, deceleration, the gyroscopes, and also the GPS position, magnetic, north pole and true north pole. This is this small switch. We have the thrust asymmetry compensator, the primary flight control computer, the APU start like this, the battery, the left engine, right engine, the backup generators, and the bus tire switches for the electric system. The passenger oxygen, the window heat, the rammer turbine. This is the hydraulic fluid. I will disconnect now to show you what happens. I'm gonna have some fault for the hydraulic over here. Now it's coming up, and you will see down here we have alternate now flaps. We're gonna lose the stabilizer, this red flight controls, and the hydraulic pressure, R, L, and C, all three of them. So we need to restart the hydraulics, the left engine and the right engine, and the electric and pressurized by air system. So this is the lighting system of the aircraft, the left and right windshield wipers, the fire control, the electronic engine control for the engine left and right, the auto start, I don't know, you can leave this on. We have the normal and the alternate system. We have the arm for dumping fuel in flight, and select the nozzles, select how much fuel on board, the crossfeed valves, the fuel pumps, the sender, it's empty, you can see the yellow, and the left wing, the right wing, the RDIs over here, the cabin pressurization system, auto, manual. We use the outflow valves for climb or descent. We open and close the outflow valves and select the landing altitude. This receives pressurizer, also pressurizer for wing and engine, and the ice and hydraulic fluid pressurization from the left engine and right engine. And we need the APU for starting the engines in the ground, so we turn off all the pressurized air systems. You will see the failures now over here in the upper and the lower ACAS. So we have bleed off APU, and we lose the cabin pressurization, the back pressure. Also we're gonna lose the hydraulics C1 and C2. You can see hydraulic pressure demand is lost. So we need pressurizer also for the hydraulics. We turn on again. Now we go for the engine start demonstration. One last step left, couple last steps, and we have like 5 more minutes. We have the synoptics mode, the engines, the status. You can see the hydraulic, the pressure of the hydraulic, and also the oxygen, and the APU is running. The checklist I'll show you before, the normal menu before start. What we need to do, this computer will tell you. The communications, navigation, synoptics. You can see the doors are closed so the cabin can be pressurized. The landing gear, you can see the temperature of the brakes and the pressure of the tires. The left and right engine, the backup generators. You can see the voltage from the two batteries, the main 27 volts and the amperage. Also the APU is running. The hydraulic fluid, you can see where the hydraulic fluid goes. 3000 psi left, right engine and center, C1 and C2. Also the air pressurized and the throttle valve. Fuel, you can see the center tank is empty with the yellow crosses. Left wing, right wing. Total fuel on board. You can see the minimum fuel temperature where the fuel freezes -37 degrees. The left wing and the right wing, and the fuel in the left and right wing. Also the low and high pressure fuel valves, the crossfit valves, and the APU is fed from the left wing using the DC motor. We have also the bleeder from the left and right engine, the APU I showed you before. I explained already the system. So we move the thrust levers forward, you will see the drag pressure increases. We need the APU for starting the engine. And we have the last thing to show, the flight controls. You will see here everything is moving normally for the rudder, the elevator, the horizontal trim stabilizer. So all this is moving normally. There is no failure, as you can see. Both sides, also the rudder pedal. So you see here now this is working perfectly well. So we'll go back in the modes, engines. So virtual cockpit, we turn off both engines and start them again. Turn off both fuel shut-off valves. We have the auto start on already, engine left and right. You can see the auto start. Engine shut on. So we have the fuel flow is 0 right now, as you can see here, no fuel flow. Also, if we look outside, you will see the spinners of the right and the left. Turbo fan is moving slower and now is increasing again. So you see the overhead panel, everything is reset. We can go starting the fuel in the left and right engine. So the fuel flow will increase in a couple of seconds from 0. And you can see the turbines, the turbojets right and left wing. We have them on. So one last step left before going into takeoff. Very quickly we have the menu, the FMC, the model, the position, GPS position, coordinates, 0 fuel weight, gross weight for takeoff, the reserves 5%, and the cruise altitude 35,300. The cost index 100%, minimum fuel temperature and center of gravity for cruise. Lszh is the origin and destination airport and the origin runway. Also departure arrival, Lszh 14 transfer seats, arrival Lszh 14 transmitting on transformation. The legs, cancel the discontinuity like this and activate and execute. And we have cost index 100%, 15 degrees of flap, center of gravity automatically 36%, and the takeoff speeds for this runway in this weight. So we go very quickly now. We have about 18 more minutes left for this flight. So we need to proceed into the runway for takeoff. Disarm the parking brakes, advance the thrust levers, and we go for takeoff into the runway. So you can see the runway is empty. We take the runway clearance from the traffic control and align the aircraft with the runway heading over here. Parking brakes on, the LNAV on. So you can see here the radar scan is ready, and we have the flight plan. The flaps are set. We only set the thrust over here for takeoff. So you can see where we are and where we are going over here. I have a nicer view like this for takeoff. Disarm the parking brake and go. And we have like 17 more minutes. So on 100 knots, V1, we rotate slightly like this. Be careful not to hit the runway. The pitch attitude is positive, so we retract the landing gear. Retract like this. So you can see we're climbing. You can see we are 1000 feet, 200 above the ground level, about 3000 feet above the sea level. Now we are 2500 feet above the ground, but 4000 above the sea. We climb with 7000 feet, gear speed 190 knots. We decrease the rate of climb. We have the flaps limit, and this is the stall speed warning 145. We stall at about 130 knots. We keep climbing. With this flap setting, we stall at about 130. So you can see where we are. We're gonna make a turn now, manual turn, and we have about manual flight controls right now. Now this beautiful view. You can see then the indications here. We're gonna have the runway this side, so maybe show you a nicer outside view now. You can see the airport, the runway. You can see the whole of the Zurich, and again the Galaxy. We fly with about 500 kilometers an hour, or 250 meters per second. So you may be a nicer clip. There's 1,000 feet. So now we're going into the route. Having these beautiful views over here as we keep climbing. 15,000 feet. Mach 0.47, 235 nautical miles per hour. Alright, speed. So we need to connect the first waypoint. So we're gonna have this way 16,000 feet. We're gonna have the lake. So here is the Germany in front of us, the Bayern Munich area, the Bavaria. So we have the Bayern Munich like 18 nautical miles away from us, and this is France this way, and also we have the Switzerland. From this way we have the lake. So we keep climbing. We have a beautiful view here. We have the lake here, the St. Gallen Lake and the Switzerland. We keep climbing. $30,000. And we have so we cross the first and we go to the second. Speed 200 knots. 31,000. Increase the thrust request. Also the flap setting. So we're gonna have the chemtrails now and the contrails. So here we are. We have the frozen vapors from our aircraft as we keep climbing and flying with about 200 knots. Have 10 more minutes left for this flight. Cross 33,000. You can see also here and here the thrust request. Where are you going? So we are 33,500 feet. You can see we cross now the lake over here. We're gonna cross the $34,600. We almost reached the climb altitude, and here we are. We're gonna level off at the climb altitude, 35,300 feet. And now we cruise level. Over here you have the Bayern Munich this side in front of you, the Germany in front of you, the Bayern Munich, the France in this side, and the Switzerland in this side. So we're gonna cross the lake now. Over here the Germany, and we have also the frozen vapors. So now we need to come for the turn into the airport. And we have like 8 more minutes left. We track the flaps. And we cruise over here, we make the turn like this, back into the airport. Hope you like the view. Here we have the Germany, so we have the Bavaria, and this side we have the Bayern Munich, like 18 nautical miles away. So hope you like this view of the Boeing with the frozen vapors here. And here is the Switzerland, the Swiss Alps. You can see also the frozen vapors again, and the Galaxy. So this is our spacecraft for tonight. The Boeing 777-300ER. We crossed 34,000 feet above Switzerland with about 900 kilometers an hour or 300 meters per second. So we need to go now. We are at the cruise level, we're at 35,000. And we have like 6 more minutes left for this flight. So we're cruising again manually over here. And we're gonna start the descent in a couple of minutes. Let's start descending now. So this is our spacecraft for tonight with the frozen sky over here. Now we need to set a lower altitude here and select a lower airspeed. Now we have the flight level change. And we're gonna start the descent. So here we descend, and we're going for an approach into the airport. So we have like 4 more minutes for this simulation for the video. Record time 20. So we need to keep descent. We also need to decrease the airspeed. Select some flight. And we keep descending. Also have the Vorlock. So we approach using over here. You see 104. So you can see the autopilot system selects automatically the next waypoint here as we keep descending. But we fly manually also. So keep descending. Having manual thrust also and automatic, as you can see. Increase the rate of descent. To get the runway in the right flight path. So we have a couple more minutes left for this video to end. $3,500, couple more minutes. I hope we're gonna record everything. You can see here we have the Lszh localizer, all the information, the airspeed, the radio altitude, we are 1500 above the ground level, the vertical speed, the glide slope. So we need to level off for a while, for a couple of seconds, add some thrust manually. You can see we have manual and the rudder pedals. Now align again one more time with the runway. Idle thrust now. Rudder pedals again. We're gonna level off again now for the flare. Ready? 10. Here we are. That's down. Very nice. Parking brakes and reverse. Full reverse thrust. And here we are into the runway. Very beautiful touchdown and landing. Very smooth and settled line. And you can see here we have the nose wheel over here. It's perfectly well. The tires of the nose wheel. There is no breakage or buckling of the metal. The aircraft is standing up the way it should be over here. The nose wheel, the tires of the nose wheel, also the landing gear behind. All the tires are safe. The left and the right landing gear. Both sides. And you can see also from this side again the nose wheel over here. You can see from the front. The aircraft is standing up the way it should be. All its wheels and metal parts of the landing gear. So we can use the aircraft again. As you can see, no buckling of the metal, no broken tires. So it was a smooth landing.